Hey guys, how are you all? I hope you are doing well. Okay, today we are going to resume the classes from the physical property. Okay, so the first physical property we are going to discuss today, that is melting and boiling point. Okay, so melting point and boiling point is directly proportional to mass and inversely proportional to branch. Okay, so first we will discuss some of the example for the mass, then we go for the branch. Okay, so first, say for example, if I am taking the RCl and RBr. Okay, the R is same in both molecule, but we know that, so chlorine is chlorine atomic weight and bromine atomic weight. So bromine atomic weight is more, so the boiling and the melting point is more. Second example, if I am taking the CH3Cl and CH3CH2Cl. Okay, so if you compare, so the mass of the your ethyl chloride is more compared to your methyl chloride. Okay, the third one is your isomer of haloalkane. Let's take the example of, this is your primary bromide, this is your secondary bromide, this is your tertiary bromide. Okay, so branch get increases when we moving the left to right. At the time the boiling point and melting point get decreases. Clear, right? Then we are going to compare the boiling point and melting point of the your isomer of dihaloarenes. See, if I am taking the haloarenes, this is your orthoisomer, right? This is your metaisomer. Okay, this is your paraisomer. Clear? This is your paraisomer. Okay, so in this, your paraisomer, okay, paraisomer is more melting point, but in case of boiling point all three isomers are more or less same. Okay, but in case of melting point the paraisomer is more, because in the crystal lattice your crystal lattice in the paraisomer going to fit better way, okay, compared to your ortho and metaisomer. Okay, then here itself we can discuss the dipole moment of all three isomer. Okay, dipole moment of all three isomer, we know that, right? The dipole moment, so mu is equal to distance into charge, right? So here if you take the ortho isomer, the angle going to be 60 degree. In case of meta isomer it is going to be 120 degree. In case of para isomer it is going to be 180 degree. Okay, fine. So in this case your dipole moment is inversely proportional to your bond angle. Okay, so your ortho isomer is more dipole moment, then meta isomer, then para isomer. I hope you understood well. Okay, we will go for your halo. So as I told you, your para isomer going to have a more melting point and the dipole moment is more. Okay, the next topic we will go for the density. Okay, we will go for the density. The density is directly proportional to number of carbon atom. Okay, so one is number of carbon atom, again directly proportional to number of halogen atom. Okay, then again it is directly proportional to the third one, directly proportional to your atomic weight of halogen atom. Okay, this you should understand. Clear? Say for example, if I am taking the methyl chloride and ethyl chloride, your ethyl chloride going to have a more density compared to your methyl chloride. In case of the second one, number of halogen atom, if I am taking the CH3Cl and CH2Cl2, okay, so the number of halogen atom is more, so this is more denser. Then third one is, if I am taking the CH3Cl and the CH3I, so this is going to be more dense because the atomic weight of the halogen is more. Understood. Next we going to discuss about the solubility. Okay, so it is quite tricky to understand, but I make you to explain in a simple way to understand well. Okay, so look here, haloalkane. So this is haloalkane. There is a force of attraction between that, right? Then we have a water molecule. Okay, water molecule, there is a force of attraction between that molecule also, right? Here this is hydrogen bond, right? Now there is a new bond. If I mix the haloalkane or haloarenes in the water, at the time there is a new bond formed, right? There is a new bond formed at the time the energy get released, right? This energy should sufficient to overcome the force of attraction between your haloalkane and haloarenes, and as well as sufficient to break the bond between the solvent molecule. Okay, if it's so, this is soluble. Otherwise the soluble is lesser. Here the energy released during the formation of this new bond is not sufficient to overcome the force of attraction between the haloalkane and haloarenes, and not sufficient to break bond between your water molecule, that is hydrogen bond. Clear? But in case instead of water, if I am using the other solvent like your benzene, okay, there is a force of attraction is there. So at the time if I am taking the two molecule together, mix it, after that time the energy get released, right? That energy is sufficient to overcome the bond between your haloalkane and haloarenes, and the sufficient to break the bond between the benzene. So it is soluble. Am I right? Clear? Fine. Next, one more point I have to make it clear. In case if I am taking the one haloalkane and its parent. Okay, so this is your haloalkane, CH3 CH2 CH2X. This is your haloalkane. This parent, okay, this parent is CH3 CH2 CH3 propane, right? So if you compare these two molecule, okay, the dipole interaction and van der Waals force, okay, van der Waals force greater in case of your haloalkane and haloarenes compared to your parent hydrocarbon. Okay, that is the reason why the boiling and the melting point of your haloalkane and haloarenes is going to be more compared to your parent hydrocarbon. Clear? Next we go for the chemical properties of your haloalkane and haloarenes. So first we discuss about the chemical reaction, the reaction of haloalkane. So first one is nucleophilic substitution, then elimination, then reaction with metal. So in this video we will complete the nucleophilic substitution reaction, right? Look here, this is one alkyl halide. So we know that, right? This carbon is less electronegative. It is going to be delta positive. This is going to be delta negative. Now one more nucleophile is coming. Okay, the nucleophile go and attack the electron deficient carbon. Okay, so then this nucleophile get left from your hydrocarbon. Okay, so the nucleophile which is replace the already existing nucleophile, this we call it as a nucleophilic substitution reaction. Okay, or the second definition, this reaction is initiated by nucleophile Cl minus, right? Cl minus. So the reaction initiated by nucleophile, for that reason also we can say the nucleophilic substitution reaction. Clear? Right. Next, so first I will explain to you what is exactly the nucleophile. What is exactly the nucleophile? So this nucleophile either electron rich either electron rich or it is negatively charged. Okay, negatively charged also electron rich only, but electron rich in the sense, in this case it has the lone pair of electron like this. Okay, oxygen which has the 2 lone pair of electron, nitrogen which has the 1 lone pair of electron. But in case of negatively charged one, Cl minus, OH minus. Okay, so look here, so this is OH minus, negatively charged, so lone pair of electron, water is having the lone pair of electron, then the RO minus having the negatively charged. Okay, RO minus having the negatively charged, then I minus, then NH3 having the lone pair of electron, your ammonia lone pair of electron, primary amine, secondary amine. So here negatively charged as well as lone pair of electron, here lone pair of electron. But in case of here, the oxygen is lone pair of electron, here also lone pair of electron, here negatively charged, and negatively charged. Okay, so these are the nucleophile. So in this case, one more thing we have to discuss, that is ambitent nucleophile. What is ambitent nucleophile? Right, if I am taking the alkyl halide, it is react with AgCN as well as NaCN or KCN. Here, in case of AgCN, the bond between Ag and C is covalent in nature. This bond is covalent in nature. But in case of NaCN or KCN, at the time your bond going to be, this is covalent in nature, this is ionic in nature. Okay, so if it ionic in nature, at the time there is a possibility of Cn minus, it is going to be Cn minus. Okay, so at the time, so here the alkyl halide also which has the carbon, right? This alkyl halide, your alkyl which having the carbon, right? If it is carbon-carbon bond, this is more stable compared to the carbon and nitrogen bond. Okay, so there is a 2 possibility, either it can bonded with either it can attack through the carbon or can attack through the nitrogen. But here in case if it attack through the carbon, at the time there is a stable formation of carbon-carbon bond. If it attack through the nitrogen, at this Cn bond is going to formed. Okay, compared to this, C bond is more stable. That is the reason why here there is a formation of alkyl cyanide. But in case here this is covalent in nature, at the time this lone pair of electron going to attack this alkyl. Okay, so at the time there is a formation of isocyanide. Okay, this is due to because of here in AgCN, the Ag and the carbon is covalent in nature. Clear? So this is first example. When it comes to second example, look here. If I am taking the Rx, okay, it is react with AgNO2. It is react with KNO2. Okay, KNO2. So here in this case, as we discussed earlier, okay, here in case as discussed earlier, here this is ionic in nature, this is covalent in nature. So okay, so this is ionic in nature. At the time the K plus NO2 get separated as a ions. But in case of here, this is ionic in nature, so this attack through the oxygen lone pair of electron, so then formation of alkyl nitrate. Okay, but in case of alkyl nitrate, in case of here the attack is through the nitrogen, so at the time there is a formation of nitroalkane. Clear? Right, shall we go for next? Yes. So first thing first, so this question I explained earlier itself. When it comes to the substitution reaction, okay, even nucleophilic substitution reaction, there is a 2 types, SN1 and SN2. Okay, first we will discuss about the SN1. When it comes to SN1, some of the points I want to make it clear. This SN2, the rate of reaction directly proportional to substrate as well as nucleophile. Substrate as well as nucleophile. Substrate as well as nucleophile. So your rate of reaction depends upon two molecules. Then we call it as a bimolecular nucleophilic substitution. Bimolecular nucleophilic substitution. Okay, bimolecular nucleophilic substitution. Clear? The second one is the bond breaking and making occur simultaneously. Okay, occur simultaneously. Okay, here we can use the polar aprotic solvent. Polar aprotic solvent. I will write the structure. You just name this molecule in the comment section. Okay, CH3, C double bond O, CH3. This is one polar aprotic solvent. Then one more is CH3, S double bond O, CH3. Do it in comment box. I will reply to you. Okay. Then the fourth one is your primary is more reactive than secondary than tertiary. I will explain in a great detail just sometime after. Okay. Then the fifth one is there is an inversion of take place. Inversion take place. I will tell you what is inversion. What is inversion? So as I told you, just look here. This is SN2 reaction, right? So this is your alkyl halide going to be substrate, and this is going to be nucleophile. Both of the concentration going to be depends upon rate of the reaction. Okay, so at the time it is going to attack in the back side. Okay, attack in the back side. Look here, the back side we have a 3 hydrogen. This is smaller the atom, right? If you compare the size of hydrogen, size of CH3, size of CH3, CH2. Okay, the size of hydrogen is very, very small. So at the time the OH minus will attack easily in the back side. Okay, so at the time if you take this molecule, okay, so this is the OH also connected, the Cl also connected. Okay, the OH, okay, as much as which is closer to, say for example, at initial the OH bond distance is like this. Okay, once the bond get established, the Cl bond get is broken, at the time the Cl bond length is OH, this much distance. Okay, so when the OH minus, the OH, the nucleophile which is going closer to carbon, this much time the hydrogen which is present in the backside, right, that get moved. Okay, so in this stage, this is the transition state. This is stay unstable. Why it is unstable? Because this carbon which has the 5 bond. This carbon which has the 5 bond. Okay, so this is very unstable. Once the OH and the carbon bond is established, this bond, the Cl and C bond is get broken. Okay, your product is formed. Okay, look here. So if I am taking this is the dashed wedge, this is the solid wedge. I will explain it in a great detail in the, look here. Say for example, this is your paper. So here this is just above the plane, just below the plane. Okay, if it above the plane means that should be the solid wedge. If it below the plane, that should be your dashed wedge. Okay, so if you want me to explain it in a different way, this bond, this solid wedge is towards you, this is the dashed wedge which is away from you. Okay, clear? Right. So the next one is just take. Okay, so this is your molecule. Okay, this is your solid wedge, this is your dashed wedge, this is your hydrogen. Okay, now the OH get attacked. Okay, it is going to attack the backside, right? So if it attack, at the time as much as the OH is closer, till the time the hydrogen, all 3 hydrogen going to move. Okay, so at final, once the reaction is over, just this goes to the just opposite of it. Okay, this is opposite of it, just opposite of it. Okay, this we call it as a inversion of configuration. Inversion of configuration. If you want me to give the example in a more understandable way, which is given in your book itself. So if you are using umbrella, when there is a rain, at the time there is a strong wind is coming. Okay, strong wind is coming. Okay, so this is your umbrella. Okay, now the strong wind is coming like this. Okay, at that time your umbrella become like this. Okay, umbrella become like this. Okay, just the inversion of it. What is before? The before it is like this, now it's become an inversion of it. So if you want me to draw the exactly opposite of this, so we can draw like this. Okay, okay, it become like this. Okay, become like this. Clear, right? So this is, we call it as a inversion of configuration. Next we go for the why it is not as much as speed the reaction in case of if it presents on bulkier group. Look here, this is your methyl halide, this is your methyl halide, this is your primary halide, this is your secondary halide, this is your secondary halide, this is your tertiary halide, this is your tertiary halide. Okay, so now the OH minus is going to attack. Okay, OH minus is going to attack. At the time here all three substituted groups are hydrogen, it is very smaller, but in case of here the one CH3 is bulkier, the rest of the two hydrogen is smaller. But in case of here the two CH3 are bulkier and one hydrogen is smaller. Then this here three bulkier group is there. So at the time if it more bulkier is there, there is a more hindrance. Okay, there is a more hindrance of SN2 reaction. So the fastest one is possible in case of A, then B, then C, then D. A is more reactive, then B, then C, then D. Have you understood? So we go for next. So look here. So this is what which is given here. Look here. Here there is a one bulkier group. Here there is a two bulkier group. Here there is a three bulkier group. So the reactivity is more in case of A, then B, then C, then D. Clear? Next we go for the SN1 reaction. Then we go for the SN1 reaction. Your rate of reaction is directly proportional to only substrate that is nucleophile. Only substrate that is nucleophile. So then we call it as a unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. Your substrate nothing but your alkyl halide. Clear? Then there is a formation of intermediate. It means that there is a two-step reaction. There is a step 1 that is bond breaking. Bond breaking is a step 1. Bond breaking, the formation of intermediate. Formation of intermediate. That is first step. The second step is bond making. Bond making. So bond breaking and making occur separately. So there is a formation of intermediate. I will tell you why there is a intermediate formation. Okay. Then there is a third one is the intermediate formation, the bond breaking, because of we are using the polar protic solvent. Polar protic solvent. I will write the molecular formula. You just comment the name of this solvent. Okay. So H2O, then your CH3 CH2OH, then we have CH3 COH. Clear? So in case of your SN1, your tertiary is more reactive than secondary, then primary. Then the fifth point, here there is a formation of racemic mixture. There is a formation of racemic mixture, so we can say racemization. Okay, these are the five points you should remember. Now I will explain the SN1 reaction in a detailed way. Okay, so look here. So in this case, here this is the alkyl halide. So alkyl halide, when we mix with polar protic solvent at the time there is a bond breaking, there is a formation of carbocation, and this reaction is reversible nature, because if this symbol is come, you know very well this is reversible. It means that alkyl halide will form the carbocation, again the carbocation will form the alkyl halide, right? Then this is the bond making. Okay, this step is slow step. This step is slow step. This is the fast step. Okay, slow step. This step is faster one. Okay, slow step and the faster one. So your reaction rate depends upon only this step. Okay, so that is the reason why only the substrate, okay, substrate one concentration only determine the rate of the reaction. So the rate of the reaction depends upon the concentration of substrate alone. Clear? So I want me to explain to you this one. If I am taking the CH3 CH2 plus, okay, it is formed from the your primary alkyl halide. In case of next one alkyl halide, this is secondary. So this secondary halide going to form the your secondary carbocation, right? This is your secondary carbocation. In case of this one, this is tertiary carbocation, right? Okay, tertiary carbocation. So if you compare the hyperconjugation for this molecule, the hyperconjugation nothing but number of alpha hydrogen. Here this is alpha carbon, this is 2 alpha carbon, this is 3 alpha carbon. So here there is a 3 alpha carbon, so 3 hyperconjugation, 6 hyperconjugation. Okay, for this one 9 hyperconjugation. Okay, so your tertiary carbocation is more stable than secondary, then primary. We know that the number of hyperconjugation directly proportional to your hyperconjugation, right? Okay, so your stability. So here in this case, if I'm taking the tertiary alkyl halide, at the time there is a ease of formation of tertiary carbocation. Why? Because your tertiary carbocation is more stable compared to your secondary then primary. Okay, so if I am taking the tertiary alkyl halide, there is a ease of formation of tertiary carbocation and the reaction of SN1 reaction also faster. Okay, the next thing I want to explain to you is, if I am taking the allyl halide and the benzyl halide, if I am taking the allyl halide and the benzyl halide, look here, this is very important. CH3 CH double bond CH CH2 X. Can you comment what is allylic halide? Your halogen bonded with the sp2 iodized carbon that is attached to carbon-carbon double bond. Okay, so in this case, what is the formation of carbocation? This is your carbocation formation, right? This carbocation, if this pi bond is moved here, this positive charge will come here. Okay, so positive charge will come here. So this is resonance stabilized, right? Like this. Your benzyl halide also, this is CH2Cl, right? So your X bonded with your halogen bonded with the sp3 iodized carbon that is attached to your aromatic ring or benzene. This we call it as a benzyl halide. The benzyl halide will form the benzyl carbocation. Okay, so this also resonance stabilized. If your carbocation is more stable, then this will undergo the SN1 over the SN2. Clear? Fine. We will solve the question now. Okay, so the first question first. They given the cyclohexyl chloride. They given cyclohexyl chloride. Then one more compound which given. Now we can discuss. Look here. This is one halide which is given. So it should be not aromatic, right? So this is one compound. This is chlorine, right? So this is another compound. They are asking which one is faster in SN2. Clear? So this is primary, this is secondary. Obviously the primary is more reactive in case of SN2, right? The next one is your alkyl group is same but halide get changed. Your alkyl group is same but halide is changed. So if you compare the iodine and the halide, your iodine is easily leave. Okay, so good leaving group compared to your Cl. So your Cl containing compound is more reactive compared to the iodine contained compound is more reactive compared to the Cl1, right? This is the first question. We will go for the second question. Look here. So here there is a any molecule which is given here, that is isomer of butane. Okay, so 1 2 then 3 then 4. Okay, it look like this is same, this is same. Now we are going to substitute the halogen. Okay, so halogen we can substitute here, we can substitute here. Halogen we can substitute here, we can substitute here. Okay, now this is primary, this is secondary, again this is primary, this is tertiary. When it comes to SN1, we know that the tertiary is more reactive, but in case of SN2, your primary is more reactive. Okay, now the thing is, tertiary is more reactive than secondary than primary. Okay, now these two are primary, right? Number one, this also primary, this also primary. Okay, so we can look at this two alkyl halide in the perspective of SN1. According to SN1, your halide attached carbon, okay, halide attached carbon, okay, in that carbon, if there is a bulkier group on that carbon or near to that, okay, so in that carbon is not bulkier group, okay, so not attached, but in this carbon there is a 2CH3 group. Okay, so this also the plus I effect also there. Okay, but in case here near to that carbon only one methyl group is there. Okay, that is the reason why if I am taking the A, B, C, D. Okay, so in that case if I am comparing the A and C, the C is more reactive in SN1 and A is less reactive. Okay, clear? But in case of your SN2, A is more reactive than C, then secondary, then tertiary. Clear? Okay. Next we go for another molecule, that is all are benzyl halide only. All are benzyl halide only. Look here. Benzyl halide. C. One benzene connected with CH2Cl. Then one benzene connected with CH3 CHCl. Then third one which is connected with 2 benzene, the Cl. Then fourth one it connected with 2 benzene and 1 methyl halide. Clear? So if I look at all the benzyl halide, okay, this is your primary, this is secondary, this is also secondary, this is tertiary. Okay, so A, B, C, D. Okay, so if it more benzene group is there, more aryl group is there, more resonance structure is possible, then more stable, then it undergo the SN1 reaction. Okay, so if you compare the B and C, both are secondary, but in case here there is a presence of one alkyl, one aryl. But in case of C, there is a 2 aryl group is there, so 2 aryl group is there, more resonance is possible. So this one, okay, the C is in SN1, C is more dominant compared to the B. Okay, so the most reactive one in case of SN1, your tertiary, so D is more reactive. If you compare the B and C, the C has the two phenyl groups, so more resonance. So your C is more reactive, then B, then A. Clear? So in case of SN2, so this is more bulkier, right? This two phenyl group are more bulkier compared to one phenyl and CH3. Then in SN2 cases, the B is more reactive compared to the C. Then your reactivity going to be A is more reactive, then your B, then your C, then your D. Clear now? Thank you all. Thank you for watching my video. Okay, we will meet in another great video. Okay, that the topic is stereochemical aspect of nucleophilic substitution reaction. Thank you. Take care.